A NASA spacecraft is set to make history today, getting closer to the sun than any other human-made object. The Parker Solar Probe must survive the radiation and extreme temperatures it will encounter.
Our sun in all its fiery splendour. We've been studying it for centuries, but there's still so much we don't know about it.
3, 2, 1, 0.
NASA's Parker Solar Probe blasted off in 2018, heading to the centre of our solar system.
What if the sun, the one thing we trust to remain stable, is actually far more chaotic than we ever imagined? Nikki Fox, NASA Science Mission Directorate, once said, "Flying this close to the sun is a historic moment in humanity's first mission to a star." And today, we're going to understand exactly what that meant. Because for the first time in history, humanity didn't just observe the sun, it entered it. What scientists found was not a calm, glowing sphere, but a shifting, unstable system, a surface that twists and bends, magnetic structures forming, stretching and collapsing. Patterns that don't behave the way we expected. And to understand why this changes everything, we need to go back to what we thought the sun really was. For most of human history, the sun was seen as constant, predictable, reliable. It rises, it sets. It powers life on Earth. Every system we depend on, climate, seasons, even modern technology, is tied to it. That simple image started to break with one mission. NASA's Parker Solar Probe, a spacecraft designed to do something no machine had ever done before: get closer to the sun than ever imagined, and eventually enter its outer atmosphere. This wasn't observation from a distance. This was direct contact, a journey into a region where temperatures reach millions of degrees, and where physics itself starts behaving differently. And what Parker found wasn't what anyone expected. The sun's outer atmosphere, the corona, is where things begin to feel strange, because the corona is hotter than the surface below it. Not slightly hotter, but dramatically hotter. That alone challenges basic logic. Now, scientists believed there was a boundary, a clear transition between the sun and the solar wind. This boundary is called the amplifying critical surface, and on April 28, 2021, Parker crossed it. For the first time in history, a spacecraft was no longer near the sun. It was inside it. What it found was not a clean, stable boundary. It was irregular, uneven, constantly shifting. At times, Parker moved in and out of it repeatedly, as if the edge of the sun itself was breathing. Think about that. We imagine stars as stable spheres of energy. This discovery suggests something very different. The sun's outer layer behaves more like a turbulent ocean, waves of energy rising and falling, constantly reshaping the boundary itself. And that forces a bigger question. If the boundary isn't stable, then what else about the sun have we misunderstood? As Parker moved deeper into the corona, it encountered something unexpected, structures known as pseudostreamers. Outside these regions, chaos, high-speed particles, energy moving in all directions, a constant, violent flow, but inside everything changed. The environment became quieter, fewer particles, less intensity, a noticeable drop in activity. Scientists described it as entering the eye of the storm, calm, surrounded by chaos. And this wasn't a one-time event. It happened again and again, which suggests something important. The sun is not uniformly active. It's structured, layered with regions of intensity and regions of relative calm, existing side by side. That means solar activity isn't random. It's organized, controlled by underlying systems we're only beginning to see. So now the question becomes, what is actually creating that structure? Then Parker detected something even stranger: sharp, zigzag patterns in the sun's magnetic field. These are called switchbacks. At first, scientists thought they were rare anomalies. But as more data came in, a different picture appeared. They were everywhere, frequent, repeating, and stronger closer to the sun. And here's the key detail. They seem to originate from the sun's surface, from a region called the photosphere. This suggests that something deep within the sun is generating these patterns and sending them outward, possibly through magnetic funnels, channels where energy is forced upward, twisting magnetic fields along the way. The result? A magnetic system that is anything but stable. It bends, it folds, it snaps back, constantly changing shape. And this matters more than it seems, because the sun's magnetic field controls how energy travels through space. It drives solar wind, it affects radiation, and it directly influences Earth's space environment. But these switchbacks may also connect to one of the biggest mysteries in solar science. Here's the paradox. The sun's surface is extremely hot, but its atmosphere is even hotter. That shouldn't be possible. Normally, heat decreases as you move away from its source. But the sun breaks that rule. For decades, scientists couldn't fully explain why. Now, Parker is giving us clues. Those switchbacks, those magnetic disturbances, suggest that energy isn't moving in a straight path. It's being redirected, transferred, possibly even amplified. Two major processes are now being studied: plasma waves, energy moving through charged particles, and magnetic reconnection, where magnetic fields collide and release bursts of energy. Both could be feeding heat into the corona, and for the first time, we're not just guessing. We're measuring it. This is the part most people never hear about. We're not just learning new details about the sun. We're changing the fundamental rules of how stars behave. The sun is not calm, not stable, not predictable. It is dynamic, unstable, constantly evolving. Its atmosphere is uneven, filled with shifting boundaries and hidden structures. Its magnetic field is powerful and far more complex than we imagined. And this isn't just about the sun. These forces affect satellites, communication systems, and the space environment around Earth. But more importantly, they change how we understand every star in the universe. Because if our own star behaves this way, what about the billions of others? So the next time you look at the sun, remember, you're not looking at something simple. You're looking at a system we are only just beginning to understand. And what we discover next might completely reshape how we see the universe.